So welcome to this new lecture on mechanical vibrations, and today we're going to discuss about the solution of second order linear non-homogeneous ordinary differential equations. And this is the underlying equation of motion of forced vibration problems. That is the topic of chapter number 3 of your textbook. So before going into the details of forced vibration and looking at the responses, we have to first go through the solution procedure of second order linear non-homogeneous ordinary differential equations. And if you remember that in chapter number 2, we discussed about the response of a second order linear homogeneous ordinary differential equations. Okay, so in case of linear uh, homogeneous differential equation, this term, that is a function of time ft, will be 0. But if we are dealing with we are dealing with linear non-homogeneous ordinary differential equation, then this ft will not be equals to 0. And so this ft is not a function of x or any of its derivatives here on the left hand side. So this term, you can consider it as an alien term. That is why this term makes the equation non-homogeneous actually. In general, this function ft can be periodic, it can be shock or impulsive function, it can be a random function, a polynomial, exponential, a trigonometric function, harmonic function, and also any combination of these functions. So it's a very general equation 1. Okay, and I have written it in form of the vibration parameters. So this is the complete uh, equation of motion of vibration, including the damping term as well as the stiffness term, the inertia term. And so the solution of equation number 1, okay, will be composed of two parts because it is a non-homogeneous second order equation. So the complete solution, general solution of equation 1, will be composed of two parts. The first part is the homogeneous part that we have solved in chapter number 2, and you have seen how to get the response of homogeneous second order differential equations. That is, their solution depends upon the roots of the characteristic equation. So if you are solving this equation number 1, you have to get that solution, that homogeneous part, and then you have to get the particular solution. That is, you then have to consider this whole equation and solve it, including the function ft. So that solution will be the particular solution, and if you consider ft equals to 0, that solution will be the homogeneous part of the solution. So as you all know that the homogeneous part that we have obtained in chapter number 2 were all diminishing in time. If they are stable responses, they will all diminish in time. So the the homogeneous part will be transient. We call it transient part, okay? And this transient part will going to decay after some time, or will going to vanish after some time, leaving behind only the particular solution that is due to the applied excitation on the system. So this excitation is never uh, removed from the system. It acts there continuously, and therefore the particular solution is a steady state solution. So in terms of non-homogeneous differential equation, we call the particular solution as the steady state solution, whereas the homogeneous solution as the transient solution. Now in chapter number 3, that is forced vibration, we will going to assume that the homogeneous part of the solution will not going to be dominant, okay, and it will not going to play a significant role in the total solution. Therefore we are only concerned with the particular solution, and we ignore this homogeneous part of the solution. However, you should remember and keep in mind that there can be certain cases in which the homogeneous part of the solution will also remain significant. That is to say that it will not going to decay or diminish with time very fast. Okay, it will going to have some appreciable time so that it can in some manner affect the totality of the solution. Uh, but So for the time being, we're going to assume that this homogeneous uh, part of the solution is not that dominant. And so we are only concerned in finding out the solution XP. So equation number one is therefore known as the governing differential equation of motion for forced vibration systems. And in this chapter, we're going to consider this function of Ft as harmonic only. Okay, so we're going to consider it as harmonic excitation function. So of time, of course, which can be in terms of force, moment, or displacement. So this function of time will be harmonic, and harmonic functions are periodic functions, so it will be harmonic function, and it can be in term of the applied force, that is a force, a continuously applied force on the system. It can be in term of a torque, okay, harmonic torque, or it can be in term of a displacement, harmonic displacement. So there are two popular methods to solve this type of ordinary differential equation. That is the method of undetermined coefficients, and secondly the method of variation of parameters. So we're going to consider the method of undetermined coefficient. We're going to use the method of undetermined coefficient to get the particular solution of equation number one, which is the second order linear non-homogeneous ordinary differential equation. Now, this method of undetermined coefficient is pretty simple to understand, and it works very well if the excitation function is a function of sine, cos, it might be a polynomial function, and if it is a exponential function. So this method of undetermined coefficient will going to work very well if this ft is any of these functions. It's function of sine, cos, polynomial of some degree, and maybe exponential, and also their combinations. Okay, so you can have something like this as well. For example, this excitation function can be given as the polynomial function bt square into the trigonometric function of cos. So cos 80 can be any combination as well, plus maybe the exponential function. So for all these kind of functions, this method of undetermined coefficient works very well. And what is the underlying idea behind this method is that uh, we, we have a good look at the form of ft, okay, and since we have made it very clear here that we're going to consider harmonic function as long as we are dealing with forced vibration in chapter number 3, then this ft will be a harmonic function. So we look at the form of this function, okay. For example, the excitation function is given like this. This is a harmonic function, f cos omega t, where f is the magnitude of force, applied force, and omega is the excitation frequency. Please remember that omega is not the natural frequency of the system, it is the applied excitation frequency. So if the excitation function is given like this, then by looking at the uh, function ft, the form of the function ft, we can assume a solution. So we assume a solution such that we say that the response uh, of this equation 1 can be written as capital X cos omega t, where this omega and this omega are the same thing, and this x is the amplitude of forced vibration, the amplitude of forced vibration. So please remember that this x is not equal to this f. This x is not equal to f, so we need to find x. And we say that this x is the undetermined coefficient. This x is now our unknown undetermined coefficient, or undetermined coefficient, or unknown coefficient, and it's a constant. So we have to now find the value of x. So how we will going to find the value of x? We are going to substitute this response function that we have assumed by looking at the form of this excitation function. We're going to substitute this value in this equation. So we're going to have a double derivative of this function, a single derivative of this function, and then substitute here. Okay, substitute the value of ft, which is f cos omega t, and then try to find the value of this capital X for which this equation is satisfied. This is known as the method of undetermined coefficient. So simply we can say that by using the concept of undetermined coefficient, the mathematical form of the response function will be similar to the mathematical form of the excitation function. It will be similar but not same. So having this idea in mind, we move towards the response of 1 degree of freedom undamped forced vibrations. So in this case, we are using a system that is undamped, and on this system there is an excitation function being applied, which will not be removed from this system. It will always going to act there, and this function of time ft will be harmonic. So formally you can define forced vibrations are vibrations where an external excitation, okay, so this is the external excitation, the function ft. So force vibrations are vibrations where an external excitation in form of maybe force, torque, moment, or displacement is continuously applied to the system. And there can be many real world examples of forced vibration. For example, the continuous motion of this forging machine tool, and for example the measurement of the vibration uh, using this sensor, this MEMS sensor. So this sensor is attached with this cantilevered beam, okay, and then this beam is being struck by some kind of a force or hammer, and it vibrates, and that vibration is uh, is picked up by this sensor, okay, and the infrastructure inside this sensor, okay, starts picking up those vibrations, and it measures the response. So the infrastructure in this sensor is receiving vibration from its base. The base is the cantilever beam on which the sensor is attached. So this becomes a forced vibration problem. So sensor attachments or recording vibrations experimentally is a very good example of forced vibration. Machine tools like lathe machines, milling machines, and forging hammers, they all are examples, can be good examples of force vibration. Unbalanced machines or rotors like engine, pumps, compressors, fans, blades, uh, these all can be examples of force vibration. Earthquake and vibration of automobiles on rough tracks, these all are examples of force vibration. So in a simplified manner, we assume an inertia element, okay, which is a compulsory element of vibration problems. So we assume an inertia element, and on this there is a spring attached. So this is an stiffness element, okay, and then there is a excitation function being applied continuously on this system. That can be anything. It can be force, moment, it can be displacement, but what we are assuming is that this ft is harmonic. It's some kind of a harmonic function, as shown here. So it is harmonic, and we will stick with this assumption that these excitations will always be harmonic as long as we are dealing with chapter number 3. So you can draw the free body diagram of this system. Okay, this force is acting on this inertia element, it is trying to bring it down. So this is the positive direction of the displacement, dynamic displacement amplitude. Okay, this force is acting in the downward direction, so the recovering force of the spring will going to act in the upward direction. And what you need to do is that you need to use this Newton's second law in translation in the y direction, because forces are acting in the y direction, the motion is in y direction. So we have to use the Newton's second law in translation in y direction. That is mx double dot plus kx equals to this this excitation function ft, which is equal to f naught cos omega t. So this is our the governing differential equation of motion, and it is, you can see that it has the same uh, form like this, uh, with this damping term to be 0. Okay, so this is a second order linear non-homogeneous differential equation of motion. And from the method of undetermined coefficients, the particular solution can be written as xp as a function of time equals to capital X cos omega t. So you can see that we have assumed the same form, the same mathematical form as the given harmonic excitation. So this is also harmonic. If the input excitation is harmonic, the output is also harmonic. And with this x as an unknown, and please note that again omega is same. Okay. So when you will apply a forcing function or excitation with a frequency omega, your inertia element, that is this mass, will start vibrating with the same frequency omega. So in this equation we have to find x, okay, such that it satisfies the given equation of motion, that is this equation 1. So we differentiate this with respect to time once, and then we differentiate it with respect to time twice, and then we substitute all these derivatives in equation 1, and then compare the coefficients of cos omega t. So if we compare the coefficients of cos omega t, an expression for x can be found out, and that expression is this one. So we came to know that this amplitude of forced vibration, undamped forced vibration, is equal to f naught, that is the magnitude of the applied force, upon the system parameters, some function of the system parameters, that is k minus m omega square. So k is the stiffness of the system, m is the inertia of the system, omega is the excitation frequency. And so x can be written as f naught upon k minus m omega square. Now this expression of x is very simple to remember, okay, and this can be actually converted into a dimensionless form by defining these ratios. So what we have to do is that we have to take this k common from the denominator, so that we can write it in the numerator as f naught upon k. So we see that f naught upon k is actually delta st, which is the static spring deflection. So you can consider this ratio uh, as you have a spring of the stiffness k, and instead of applying the dynamic uh, function on this spring, you apply a static value of the force that is equal to the F naught, this F naught. So when you will going to do this, what will happen? The spring will going to stretch by some amount, and that amount is the static deflection. That is simply the static deflection. So F naught upon K, if K is the stiffness of the spring, then F naught upon K is delta ST, that is the static spring deflection. If you divide omega with omega n, okay, because when you will take this K common from the denominator, it will appear here m over k in form of m over k. So m over k is 1 upon omega n square. Okay. So you will get omega upon omega n whole square here. So we say that omega upon omega n is R, which is known as the frequency ratio. So these are the terminologies of forced vibration systems. Static spring deflection F naught upon K delta ST, omega upon omega n R, which is the frequency ratio. And we can actually define another ratio which is dimensionless. If we bring this delta ST here as the denominator of x, okay, then this is known as m, the magnification ratio. So you can consider magnification ratio as the dimensionless amplitude of forced vibration. So therefore our particular response for this 1 degree of freedom undamped force vibration problem becomes x into cos omega t, where x we have already found out, it is equal to f naught upon k minus m omega square. So f naught upon k minus m omega square cos omega t is the particular response. But you should know here that the total response, okay, the total response of this forced vibration, undamped forced vibration system also includes the response, the homogeneous response. However, we have assumed that this homogeneous response is not dominant, but there can be cases in which this homogeneous response can be dominant. That is, uh, it might be such that this response takes a very long time to decay, and therefore, in that case scenario, it will be important to include the homogeneous solution as well in the total solution. But for now, for the time being, we consider this part to be not important, and we say that the particular response is xpt, which is this value. So now, as I already told you that we can define a dimensionless amplitude, that is x upon delta st, and so this omega upon omega n can be considered as r. So this means that x upon delta st, which is equal to m, the magnification ratio, will be equal to 1 upon 1 minus r square. So you can note that m is only a function of frequency ratio here. That is to say that in undamped force vibration problem, the magnification factor or the magnification ratio is only a function of frequency ratio r. So depending upon the value of the frequency ratio r, we have certain cases to deal with. Now the case number 1 represents when this value of r is greater than 0 but it is less than 1. Okay, so if you have a horizontal axis on which you define the value of frequency ratio r, and the vertical axis where you define the dimensionless amplitude, that is the magnification ratio or magnification factor, okay, you can plot this function. Okay, you can substitute the value of r between 0 and 1 and you can see how m is behaving. Okay, so if r is greater than 0 but less than 1, the denominator of this magnification factor will be positive, okay, because this r is either 0, this r is either 0 or it is less than 1. So therefore this function is positive, uh, and therefore it will be plotted in the positive quadrant, okay. The function will be plotted in the positive quadrant, and you can see that it is actually increasing. It is actually increasing as r increases from 0, and when r reaches 1, okay, the dimensionless amplitude, that is the magnification factor, increases to a very high value. Theoretically, it will become infinite, okay. Mathematically it will become infinite if you substitute r equals to 1 here. So that is why this curve is actually increasing, and it's increasing at a faster and faster slope if r is reaching 1. So we see that the response, that is x cos omega t, will be exactly in phase with the applied excitation. So that is also visible here. You can see that uh, this input excitation is cos omega t, and this output response is also cos omega t. So there is no delay or lag. Therefore we say that the response is directly in phase with the excitation. And so in phase with the input excitation means that uh, when this excitation input function will reach its maximum value, the response will also reach its maximum value. So therefore the inertia element and the excitation function both will be in phase. They will move in the same direction. So when f will be positive, this response function or the displacement of the inertia element will also be positive. And as this f becomes 0, or it becomes negative, reaches to its negative maximum, then the response also becomes 0 exactly at the same time without any delay, and it reaches its negative value exactly at the same time. So you can see that they are exactly in phase at each and every point. Okay, so this is how your magnification factor will behave between r equals to 0 and 1. That is the frequency ratio between 0 and 1. So if you are uh, closer to 1, m is equal, closer to 0, m is equal to 1, okay, this means that uh, the amplitude x is equal to the static deflection of the spring. But as soon as r starts to increase, the value of x increases from relative to this static deflection of the spring, and it reaches very high value as r reaches 1. Case number 2 will be when r is greater than 1. So you if you look at the expression of the magnification factor, you will see that when this r is greater than 1, then the denominator will be negative, okay. So the curve will now start from the negative y-axis, and you can say that the response is now 180 degree out of phase with the applied excitation, because we have now here a negative sign because of this denominator getting negative. So the response xt will going to get negative. This means that out of phase, 180 degree out of phase. So this is the region. You see that when r is greater than 1, okay, what will happen? So we will start from r is equal to 1 actually, and when r is equal to 1, this acquires a very high value. So we start from somewhere here at a very high value, and now from this point onwards, when r increases, it becomes greater than 1. What happens? That this value becomes smaller and smaller, because this denominator is increasing as the value of r is increasing. So this curve starts to reach 0, and as r increases farther and farther from 1, this amplitude, the magnification factor, approaches 0. So you can see that uh, this is actually very close to 0, and it is getting closer and closer to 0 as the value of r will going to increase. So we see that r increases, that is when r becomes infinite, x tends to be 0. Okay. Therefore, response to harmonic excitations of very high frequency is close to 0. Now this is, we can say that it's a good result, because uh, as we increase the excitation frequency, as we increase the speed of the machine, okay, its vibration amplitude tends to get lower and lower. But high rpms, high speeds, or high frequencies means greater material fatigue. So material fatigue at very high excitation frequencies can be an issue. But as far as the vibrations are concerned, the amplitudes of forced vibrations are concerned, they will going to get reduced if the frequency of excitation is increasing. So 180-degree out of phase means that when the input excitation is at its maximum, then your response will also be maximum, but it is negative. But it will be negative maximum, you can say. And when it becomes 0, passes from its equilibrium point or 0 point, this function, the response will also pass from 0. As this will become, it will going to reach its negative maximum, then the response will reach its positive maximum. So the inertia element in your vibratory system will move, uh, opposite, will move in the opposite direction relative to your input excitation. That is what this negative signifies here. So case number 3 is when r is equal to 1, and when r is equal to 1, you will see that that this magnification factor will be mathematically infinite, and actually you cannot calculate that. So this case number 3, which is r equals to 1, represents resonance, and we know that resonance is to be avoided, and at least if we cannot avoid it, we have to use some special means of damping to limit the amplitude of vibration near resonance. Okay, so now we cannot actually use this response, this kind of a response, when we are operating at resonance. Okay, we cannot use this kind of a response. So there is another response given here, that the particular response at resonance can be uh, estimated from this expression. Okay, and this expression is obtained by considering the total solution of the force response, that is the homogeneous part plus the particular part, and using Del Hospital rule in the limit when omega reaches omega n. So we know that r is equal to omega upon omega n, and in the limit when omega reaches omega n, then r will will tend to be 1, and when it tend to be 1, this magnification factor will be infinite. So therefore a special arrangement has to be done by using the Del Hospital rule and considering the entire total solution, that is the homogeneous part plus the particular part, to obtain this response function. And this response function is only valid for resonance. Otherwise we can use these responses. So valid only for resonance. So we approach to the response of 1 degree of freedom damped forced vibrations. Okay, now this time we are dealing with the damped forced vibration. And a damped forced vibratory system would look something like this. We have an inertia element M, we have a stiffness element K, we have a damping element now C attached to the mass, and the same excitation Ft is acting on the mass. The positive direction of the displacement is downward, and so the recovering forces of the spring and damper will going to act in the upward direction. So we have applied a harmonic force excitation, because we have already claimed that the excitation function Ft will always be harmonic. A viscous damper is also implemented now. So if you use the Newton's second law in translation and in the y direction, you will going to get this kind of a equation of motion. This is the second order linear non-homogeneous differential equation of motion, with the excitation function still harmonic. So we assume that the particular response of this equation number 1 is x, that is capital X cos omega t minus phi. Now here we cannot use the same function like the one we have used here. Okay, so you can notice that we have used a lag, a delay, and this lag and delay is because of the damping involved in the system. So we noticed that the lag in the response is due to the damping present in the system. That is if you make this c equals to 0, if you make this c 0, then this phi will also be 0, and the response will again be the same response as we have used in the case of uh, undamped forced vibration. Okay, therefore we can here claim that due to the damping present in the response of damped force vibrations will lag the excitation input by an amount phi. So due to the damping present, the response will lag. And now our purpose is to find x and phi, because this is the response, and in this response x and phi are still unknown, and we need to find x and phi. So what we're going to do is that we're going to use equation number 2 in equation number 1. Okay, so we have to differentiate this equation number 2 with respect to time once and then twice, and then substitute the values here in equation number 1, and applying some trigonometric and algebraic manipulations we can find the value of x and phi. Now these are the same steps that we did in this case. Okay, we get the first derivative of the solution, we get the second derivative of the solution, then we substitute those solutions here in this equation 1 and get the value of x by comparing the coefficients. So the same thing we have done here, but additionally what we will going to do is that we're going to use some trigonometric manipulation, that is the formula of cos alpha minus beta and sine alpha minus beta uh, during our solution. And we have to use some algebraic manipulations as well, maybe solution of simultaneous equations and something like that, and we can get the value of x and phi. So if you compare the value of this x with the value of x that we received in the undamped force vibration problem, okay, that was f naught upon k minus m omega square. So this was the amplitude of forced vibration when the system was undamped, and if you compare this result with this one, you will see that this k minus m omega square again appears in the denominator here. F naught is already there, and there is an additional term appearing here, and this additional term is because of the damping present in the system. So if this C becomes 0, then you can notice that again you are going to get this same result. So the value of X in case of 1 degree of freedom damped forced vibration is given by this expression, and the lag is tangent inverse of this divided by this. So once we get the value of X and phi, we can substitute here in equation number 2, and we get the particular response of the our inertia element, that is the response of damped forced vibration. Okay, so consider uh, the value of X here again. Okay, and what we do is that we take K as common from the denominator and use the following substitutions. So we know that omega n is K upon m under root K upon m omega n. C is equal to 2 times zeta m omega n. Okay, because we know that zeta is equal to C upon Cc, whereas Cc can be written as twice mass times omega n. So using these definitions, we can say that C is equal to 2 zeta m omega n. Omega n is already known to us under root K by m. Static spring deflection is already known to us. It is F naught upon K. R is the frequency ratio omega upon omega n, and we have already claimed that the dimensionless vibration forced vibration amplitude, that is x upon delta st, is equal to m, the magnification factor. So if we take this K common from the denominator, take it in the numerator, and then use these substitutions in the denominator, we will going to get the expression for magnification ratio or magnification factor in case of damped force vibration as given in this boxed expression. And so if you compare this result with the previous result, you will see that how it differs from the previous case. In the previous case, m was 1 upon 1 minus r square. So it was only the function of frequency ratio. But here you can see when you are using damping in your system, forced damped vibrations, then this m is a function of r as well as zeta, where zeta is the damping ratio, you all know. So now the magnitude of forced vibration or the amplitude of forced vibration depends upon the frequency ratio r and the value of zeta, and we know that zeta can assume values that can be greater than equal to 0 and less than, oh sorry, it can be greater than equal to 1. So it can be critically damped, it can be over damped, it can be under damped, whatever. So this means that we can plot the values of m by assuming values of r and zeta. Okay, so for different values of r and different values of zeta, we can plot this function and we can see its variation. So if you look carefully this figure, this is the last slide by the way of this lecture, so, and it's very important one as well. So the magnification uh, factor or the magnification ratio, or you can also say it as amplitude ratio m equals to capital X upon delta st. It is plotted on the vertical axis, and on the horizontal axis we have plotted the frequency ratio. Okay, and both are dimensionless, and for different values of zeta these curves are plotted. Okay, so looking at this diagram, we can this graph, these graphs, we can actually sum sum up few points here, some important points here. If you go through one by one, them you will see. So you can first observe that at zeta equals to 0, which represents the undamped case, m increases infinitely at r equals to 1. So this is the value of r equals to 1. This arrow indicates r equals to 1, and you see that all these curves have been assigned some value of zeta. Okay, and this one is zeta 0.1, and already it has reached a very high value. So zeta equals to 0 will mean that the curve will be higher than this one. So this means that the magnitude, sorry, the amplitude ratio or the magnification ratio becomes infinite at r equals to 1 if your system is not damped. You can also observe from this curve that from these curves that critical and over damped cases, for critical and over damped cases, m always decreases with increasing values of r. So you see that this curve here is plotted for zeta equals to 1, which is critical damping, and all curves below this curve represents over damped cases, zeta greater than 1, and they all continuously decreases continuously decreases as the value of r increases. In fact, they have no uh, they haven't shown any increase in their amplitude near resonance or at resonance r equals to 1. They are actually independent of the resonance. So because critical systems and over damped systems are heavily damped systems, so your structure passes smoothly from the resonance region. It does not show any increase in the amplitude. So all these curves, that is the curves for zeta equals to 1 and above 1, they continuously decreases as r increases. So they monotonically decreases. Okay, monotonically decreases means that they never increase. However, you can see that when zeta is less than 1, the curves increases, becomes maximum, and then decreases. So this is the distinguishing feature between underdamped systems when they are vibrating with some excitation force, and critically and overdamped systems when they are vibrating with some kind of an excitation input. So this suggests that the underdamped cases where zeta is less than 1 are more important in case of force vibrations. At any value of r, higher value of zeta will generate smaller m. So this is true because at any value of r, for example, we take this value of r 0.8, and we see that as zeta reduces, what is happening is that amplitude of vibration or the magnification factor, the dimensionless amplitude of force vibration, is increasing. So at any value of r, higher values of zeta will generate a smaller m. M is relatively small even at resonance or near resonance if zeta is greater than 1, right? So this we have already discussed. M also becomes small, approaches 0 when r tends to infinity for any value of zeta. Okay, and we can see this here that when r increases to infinity, to very high values, each and every curve, irrespective of the value of zeta, okay, they are trying to reach 0. So they are trying to reach 0 if r is increasing, and this we have already studied in this case, as you can see here, that when R increases, the amplitude of vibration tends to become zero, and the same thing is being actually written here, and we can notice it here as well. But however, material fatigue can become an issue. Of course, at higher values of frequency, the material fatigue can become an issue, as I told you already. If zeta is greater than 0 and less than 1 upon under root 2, the maximum value of m occurs at r equals to 1 minus 2 zeta square raised to the power half. Or you can say that r equals to 1 minus 2 zeta square under root. So you see that in these curves, you can find the value of zeta equals to zero point 0.5 and then directly zeta equals to 1. Okay. Zeta equals to some value greater than zero point 0.5 and less than 1 are not plotted. And this is because of the fact that for values of zeta, okay, greater than or equal to 1 upon under root 2, okay, there is no maximum. There will be no maximum. Okay, so these curves will remain very close to m equals to 1. So as you will going to increase the value of r from 0 to 1, okay, with the value of zeta that will be greater than or equal to 1 upon under root 2, you will not going to observe any peaks. Okay, they will all remain very close to this value of m equals to 1, and so therefore they are not shown here. So they are saying that if zeta is greater than 0 and it has any value that is less than 1 upon under root 2, because at values of zeta equal to 1 upon under root 2 or greater than 1 upon under root 2, there is actually no maximum. So for zeta greater than 0 less than 1 upon under root 2, the maximum value of m occurs at r equals to under root 1 minus 2 zeta square. So this means that this maximum of the curve shown here for underdamped cases, they are not actually exactly at r equals to 1. They are not appearing at r equals to 1. They are appearing at a value of r that is given by this expression. R equals to under root 1 minus 2 zeta square. Okay. And this is very clearly evident here, because this dotted line is representing r equals to 1. And you can see that the peaks are shown before this dotted line. So the maximum value of r, okay, or the peak value of m, sorry, the maximum value of m or the peak value of m uh, will be at r equals to under root 1 minus 2 zeta square. And if we substitute r equals to under root 1 minus 2 zeta square in this expression here, expression for m, we will going to get the maximum value of m, and that is given by this expression. So this is the maximum or the peak value of the magnification factor 1 upon 2 zeta under root 1 minus zeta square. The value at the peak of these curves, wherever these peaks are shown, is given by this expression, and this is only valid when zeta is greater than 0 and it is less than 1 upon under root 2, because at values of zeta which is greater than 1 upon under root 2 or is equal to 1 upon under root 2, there is no peak. So this is the set of information, useful information that we get from the plot of the magnification factor and the frequency ratio. And looking at these curves, we can clearly say that underdamped cases are more vulnerable uh, to achieve these maximum values of amplitude during forced vibrations. Okay, no matter if they are damped. I mean, yes. So whether you use any value of zeta, it's zero point 0.1, zero point 0.3, zero point 0.2, any value of zeta, but it has to be underdamped. Okay, then these underdamped situations will be more prone to achieve the maximum peak value during forced vibration. And as far as the critical and over damped cases are concerned, they are already heavily damped systems, so they don't show any peak in their magnification factor. So they continuously decreases as R increases. So one very important point in the end, we should note that if we are able, experimentally, if we are able to measure the maximum amplitude, okay, that is M max, if we are able to record this value M max experimentally by using some sort of vibration sensors, then what we can do is that we can estimate the damping of the structure, because we know that M max is related to this expression. So M max is equal to 1 upon 2 zeta under root 1 minus zeta square. If you can record this value, if you can measure this value using some sort of a vibration sensor attached to your structure, then you can measure the damping amount of damping present in that structure. So we're going to start the remaining topic of chapter number 3 in the next lecture. Until then, go through this lecture thoroughly, and we'll going to meet again next week. Thank you.